Okay. So keep in mind, guys, if you guys go to number 8, okay, this is one of the stuff that we talked about, right? Look at number 8. As you go from boron, this is what we talked about, boron to neon. Okay, what happens, guys? The atomic radius goes down, right, incrementally, like it goes down, goes down, goes down, right? But this is what we talked about, okay? The energy of ionization, it goes down from nitrogen to the oxygen, okay? So that's what we talked about, guys. And as I told you guys, every time the answer is what, guys? Electron repulsion, that's what we talked about, okay? So keep in mind, this is straight from the AP, guys, by the way. So keep in mind, guys, like these questions you have to know, right? All right, let's go to number 9. So the question is asking, guys, okay? So this represents the binding energy, okay? This represents and we talked about this, guys, by the way. The binding energy, guys, is what? Amount of energy needed to remove the electron from a particular like subshells, okay, like 1s or 2s or 2p, right? Without any other information, so without any other intervention, such as what? Such as like shielding or anything else, right? So we talked about this. So the question is asking, guys, okay? A sample containing atoms of carbon and fluorine, okay? So keep in mind one thing, okay? Only thing that impacts the binding energy is a nuclear force attraction, okay? So if the electron has a strong attraction for the nucleus, then it will have a strong binding energy, okay? So only thing that impacts is what? The nuclear energy. So you can see, guys, here. So the graph, I mean, so like, keep in mind, guys, a lot of times on the AP Chem, guys, so here represents intensity, right? And here is what, so this is higher, okay? And dude, this is lower. This is lower, this is higher. See that, guys? Higher and lower. So it's usually, guys, that's not really how the graph is given a lot of times, but this is high and low. So you see this, guys, I mean, so you see a big spike here, and then like, you know, a little tiny spike here, and like this, okay? So let's talk about this, okay? They're saying which of the following is a fluorine, a 1s of the fluorine, and 1s of what? 1s of what? Carbon? Carbon. So their question is asking, guys, which of the following will have greater binding energy? That's what they're asking. So the bottom represents the binding energy, okay? The bottom, right? That's the binding energy. So, okay, so binding energy should be higher for fluorine for the 1s because why? They have a greater nuclear charge, no question, okay? Nuclear charge will impact what? Will impact the binding energy. That's it, okay? So yeah, binding energy is close to like 70 here, that's close to 30, okay? So this should be the carbon, that should be the fluorine. But you have to ask yourself, guys, why is this peak higher? Why is this peak higher? What's the purpose of that, guys? Like, why the intensity is higher for this? What do you think, guys? Intensity is what, guys? Intensity is, it deals with numbers, okay? Number of like waves, okay? So what does this tell you? We get it, okay? So it takes more energy to remove electron from the fluorine. We get that, okay? Because wait, the 70 and 30, we get that. But the problem is what? The intensity is what, guys? Higher fluorine because why? There are more in the sample provided. There's more amount of fluorine atom compared to carbon atom. That's why. Okay, so it's not like 50-50. If you have like 100 fluorine atoms, 100 like carbon atoms, then what? The peak should be about the same. Okay, but because the peak is higher, what happens, guys? Yeah, probably we have what? 100 fluorines and what? Probably what? Like you know, 2 carbons. Okay, that's the reason why the intensity is shown as different. Okay, so the answer, guys, if you look at it here, the peak X should be fluorine, and peak Y should be carbon, whatever the choice just says it, okay? But you should not be concerned about the intensity. You should be more concerned about what, guys? The energy in the bottom, okay? Questions from you guys? Let's go to guys number 12. Let's see what it is. Number 12, guys, question is asking, that was a really difficult question that you guys didn't ask. It was 17. Oh, 17, yeah, you guys got one. All right, number 12, guys. For the element X represented above, which of the following is most likely expansion to the large difference between second and third? So this is one of the stuff they constantly ask you guys. So number 11, they asked this question, guys, and number, I don't know, something else, they asked this question, same thing. I don't know, it's down the road, guys. Like number 14, they asked the same question, right? They're asking why there's a jump between a second and third energy of ionization, right? We talked about this, right? So 740 for the first electron and 1,450 for the next one, and whopping 7,000 went like 6 times, right? Why did it go up? What was the answer, guys, for this one? This was due to So when there's a jump, right, that's what we talked about. When there's a big jump, first, like second and third and fourth, like if there's a big jump, what happens, guys? That means what? That means the first two are relatively simple. They're very close to each other. And third, there's a big spike, which means what, guys? Typically, atom like this as what? Two valence electrons. That's what it means, okay? So the first two are valence, and the next one is not. So whatever this thing is, what, guys? Has what? Two valence electron, which is in the what? Which probably will be like calcium or beryllium or like magnesium or something like that. Okay, one of those guys, right? So, so my answer for this one is what, guys? The electron removed the third electron is on average much closer to the nucleus. Because that's what those are inertial electron. That's not a valence electron. That's the reason why I think that's what the best answer number 12. See the answers we talked about. Okay. Any questions? Let me know for number 12. All right, the hardest question, guys, of all, I think. So you guys, number 17, right? Number 17, guys. So this is a hard question. I mean, again, so if you guys got it right, guys, great job. All right. So 17, the question is asking, guys. I mean, if you're comfortable with these questions, by the way, then I don't know, like. It's like you'd be pretty good, guys, on these exams. And aside from the other calculation stuff that we discussed last week, I mean, if you get those also as well, then yeah, like you're getting these topics. So the question is asking, guys, exothermic. First of all, you have to understand the term exothermic. I mean, this is being the AP class, by the way. I mean, you guys should know the term exothermic versus endothermic, right? Good popular term before, guys, right? What's exothermic? So the process, right? Whatever the process is what it releases energy as a product. Okay, which means the product is more stable in the reactant. Okay, it gives off energy. Okay, that's basically what we call, guys, an exothermic process. And again, the opposite is what, guys? Endothermic is what? Energy is on the reactant side. Okay, which means that energy must be put in the process to happen. So the question is asking, guys, you know, like which of the following combinations, okay, reaction is exothermic? So you got to understand, guys, this is a relatively hard question, guys, by the way, which sort of deals with what we call, guys, Hess's law. Which means, guys, you're adding two reactions and getting the resultant reaction. Okay, so, you know, so one thing to note, guys, by the way, so they got two stuff going on here. Okay, they got two of the process going on here, which is, if you look at it, guys, so X, the element X, like, you know, is what? Is losing electron. So energy must be put in, okay, to take the electron out, okay? That's the first process, right? And the other is what, guys? Other is, okay, so the other is kind of the opposite, okay? So where they're giving the electron, and what happens, guys? Turning into the element, you know, energy pops out. So that they're sort of looking at two different processes right now, okay? And they're adding it, just like Hess's law. So basically what will happen is, guys, what happens, guys? So these guys will cancel out, right? So it becomes what? The equation becomes E1, okay, plus X plus Y plus turning into Y plus X plus E2. That's the equation. You see that, guys? So whether this will be an exothermic or endothermic depends on what, guys? The value of the E1 versus E2. Okay, so whether this will be exo means what, guys? The value of energy that comes out over there is greater than E1. Okay, so meaning, guys, okay, if this is 100, if that's 200, energy perspective, then what happens, guys? Yeah, it'll be exothermic. That's what they're looking for. So if you look at it, guys, okay, so we want to have a reaction where what, guys? Where we need to have what E2 greater than what E1. Which means what, guys? I mean, it's a combination perspective, okay? E1, which is the energy of ionization for X, should be what? Lower than energy of ionization for what? For Y. So here's the one thing out here. So this one, right? So we gotta find where this one is lower than that guy. Okay, that's the process you have to look for. So if you look at it, guys, I thought the answer was, if you look at it, so I thought it was aluminum and magnesium plus. Okay, so if you look at it, so now if you look at it, guys, so there's a magnesium, which is MgE1, right? turning into Mg plus electron. That's one process, right? And now the other process, guys, will be Mg plus. I'm sorry, I messed it up. Give me a second, guys. So we have aluminum. Taking the electron out from the aluminum, Al plus electron, and this is E1. And now E2, where guys, Mg plus electron turns into Mg plus E2. That's the equation, right? So you're adding these two. So you're comparing E1 to E2, and we would like to have what? The value gets what? Smaller for E1. So if you look at from the graph, right, E1 has a lower value compared to magnesium. So if you look at from the graph, guys, and it goes up and down. So this is magnesium, that's aluminum. Okay, so which means what? This was, I put it as a E1, it's E2, which means that if you add them up, what happens, guys? Yeah, dude, it becomes, that's the equation where you'll be exothermic process, right? So this is a hard question, okay? This is a very hard question, by the way. I forgot which year this came from, guys, by the way. But a lot of students got this one wrong, okay? But I understand, guys, okay? But it has a little bit, it has a slow in it. But again, like it's one of the questions, guys, and by the end of the year, which is like next year, we probably have to know questions like this to understand what's going on, okay? Any questions, let me know, guys. Any concerns, questions, let me know? I mean, I'm not trying to, I mean, some of you guys do really well, some of you guys like, you know, but at the same time, guys, end of the year, you gotta know it all, okay? And I don't really have anything else to mention. Other than get atomic numbers, maybe, and number 15, maybe, I'm not sure. Other than that, guys, okay with these questions? Any questions there, guys? Any questions, concerns? Something you want to make comments on? Let me know. All good, guys? All right, guys. So for the next topic, guys, I'll start to discuss bonding for you guys for today. Okay. So I don't know, guys, if I'm gonna finish bonding today. It's a big topic, heavy topic for you guys. So we'll discuss bonding today and move down. All right. Okay, so bonding is a very big topic, by the way. Your teachers, guys, I mean, just bonding chapter, guys. At least your teacher will spend at least like 3 weeks on this topic, by the way. 3 weeks, guys. So I'm trying to finish in like 2 days. So, let's take a look. So the course will be, guys, we're discussing the purpose of bonding. I'm not gonna write you guys purpose of bonding, ionic bonding, covalent bonding, metallic bonding, like, you know, and also we're discussing a little bit of, guys, like internal, like the forces, of course, guys, hydrogen bonding, what it is, like, you know, and also LDF, the IMS, right, internal, like the force perspective, induced dipole, you know, and like network covalent bonds and all that stuff, guys. That's basically the discussion for today, guys. Yeah. In the chapter that's coming after this, guys, it'll be will be the gaseous chapter, gas chapter, okay? The phases. All right, so. All right, guys. So, guys, purpose of bonding, okay? So, guys, the purpose of bonding. Okay, so you guys, we talked about this, guys, a little bit. The purpose of bonding is what, guys? Purpose of bonding is for anything. Okay, for like bonding or interaction, for reaction, anything. So it could be a chemical reaction. You know, chemical reaction breaks and forms a bond. You know, it transfers electrons and all, guys. The purpose of bonding is what, guys? At the end of the day, it lowers potential energy. That's the purpose of bonding. So typically, a reaction gets promoted when the product has what? Lower potential energy, okay? It's more stable as a product. So a lot of times, guys, reaction occurs on its own. It's what, guys? This is a reactant, it's a product. Product has what? A lower energy compared to the reactant. That's the purpose of bonding, okay? So you know, so everything wants to be more stable. So you know. Like, dude, like, for example, guys, like, why, like, the atoms and the molecules, behaves very similar to how people behave. Like, you know, how things behave, guys, in nature. You know, like it's like the purpose of you guys, you know, like studying all, guys, is what? Like, is to what? Make sure you have a stable job in later time, guys, and stuff like that. So they're exactly the same, okay? Keep in mind, guys, potential energy has what? Has the stability. Lower potential energy means what? More stable, and high potential is what? It's less stable, okay? And typically, right, like at a higher level, right, stability for an atom comes as what? Stability of the atom is what? It comes typically from the octet. Okay. Which is what? The 8-electron valence shell is being filled in, right? Like typically that's where the octet comes from, right? Okay, so if you guys we talked about what octet is, right? We talked about guys valence electron being filled in, which is the SNP, the outermost SNP, okay, is what? 2 and 6. Then they're stable, okay? That's all the stuff that we talked about, guys, by the way, okay? If these are filled in, outermost SNP, oct means 8, it's what? That's ultimately what they're looking for this chapter, okay? Like how do they create the octet, okay? On the outermost shell. So one thing that the College Board kind of like, like is asking a lot is, so basically guys, for example, like, except for guys, the noble gases, they don't have the octet, okay? So they don't have enough electrons. So which means what, guys? They have to bond. They gotta interact with the other atoms and what? Either share the electrons or take the electron away to create this octet. That's the whole purpose of what? Chemical reactions, okay? That's the purpose of reaction, okay? To attain what? Stability. So you gotta understand, guys, by the way, okay? A lot of reactions that occurs on its own is what? They're exothermic. A lot of it, exothermic reactions. Like, because why? This just happens on its own relatively easily, okay? But endothermic, where like it's the other way. This is very thermodynamically not gonna happen reaction, okay? Because like they go against, like who would want to be at a higher potential energy, okay? Like same thing, like you guys want, dude, I tell you guys, like the job that I have, right? Like I work for a company that's SP200 company, right? But like, when you guys look for a company, when you guys go for a job, find a job, right? Like think about it, guys, okay? The average tenure of my company is like 15 years. So which means like if you average it up, how long they stay in the company, guys, 15 years. So like Google, for example, like an Apple, whatever, they're like 2 years or 1 year, okay? So people look at that, okay, so it's more stable, like this is a place where you can retire, like stuff like that, right? So I mean, again, like depends on what you're looking for, guys, by the way. If you're young, then it'll be a little different, guys, by the way. But again, so usually what you want to be at a more stable phase than like going here. I would not want to be hired at a company where like, oh yeah, well, I'm gonna give you like 3 times salary, but it'd be a lot more. Like I don't want that, So something like this. So this is very unlikely. Well, this is very likely the process to occur, right? So we know. So one thing to understand, guys, is this, okay? The bond, or whenever they try to bond, this is what this chapter is about. Because, okay, creating bond, whenever they create a bond, what happens, guys? They become more stable. Potentially it drops. Dude, I tell you, man, it doesn't matter what bond it is. Dude, I tell you, bond can be a lot of bonds are like, dude, there are many bonds, okay? Covalent, like, dude, like you can freaking name like 5 of these like in 2 seconds. Like covalent, ionic, metallic, hydrogen bonding, the LDF, like whatever, okay? Dipole forcible attractions. Any bond that you can possibly imagine, what happens, guys? Whenever the bond gets created in chemistry, what happens, guys? It's what? It's exothermic process. Exothermic. What does it mean, guys? It releases energy. So whenever there is a bond formed, when you hear all the bond forms, energy always releases. From the bond creation, energy releases. That's one thing to know, okay? Because what? Whenever there's a bond created, what happens, guys? They become more stable. They link up for whatever reason, and what becomes? They become more stable. So any bond, it doesn't matter what it is, guys, in chemistry perspective, guys, if you have any type of bond, okay, whatever this is, the process of creating the bond is exothermic. Okay, so if you say, oh yeah, they create a hydrogen bonding, what happens, guys? Exothermic. So the opposite direction is what, guys? Oh, if you want to break a bond, if you want to take them apart, dude, like, oh yeah, I'm gonna break hydrogen bonding, like, dude, like, water, like liquid, right? Like, I mean, it's not water, but water is what? You want to make water liquid into a gas. You're breaking hydrogen bonding. What do you guys do? Heat it up. It requires energy. You understand what I'm saying? So breaking bond is always endo. Energy must be put in. Creating a bond is always exo. You understand what I'm saying, guys? Here. So every time there's no exclusion on this one. There's no exception of this portion. Okay. And now, so what College Board they like to give you guys as a graph perspective for this bonding stuff is this. So the graph, okay? So this is more fits into the bond between the two atoms, okay? So this one represents internuclear distance, okay? So inter means between, right? Nuclear, like the nucleus of the atom. Distance, it's what? It's a distance between the two nuclei, okay? This represents potential energy, okay? So guys, I mean, I tell you, this graph, they have it a lot on the AP exams, by the way, okay? So what happens is, when the atoms are infinitely apart, okay? This atom, guys, before they make a bond, they're infinitely apart. They're like super far away. Okay, infinite, like really far. What happens, guys? Their potential energy is zero. Okay, zero potential energy, really far away. So all the students from the bio asked me a good question actually. You guys, how many of you guys come from the bio? So the equation guys, okay? Equation guys, by the way. So, like, yeah, have you ever heard this equation, guys? By the way, so a 0 bar is the water potential is highest energy. So again, like they ask, why is 0 always highest value? Because that's what they said. Like potential energy, guys, by the way, it's a very difficult to measure. Okay, because like potential energy, like measuring the potential energy, you gotta understand the definition of potential energy. How much energy is stored within a molecule or the two, like like atoms? How do you measure that thing? It's very difficult to kind of measure. Like potential energy is how much energy is stored in. Like how the hell do you measure that? So it's like measuring like your smartness. Like how do you measure a smartness of a person? Okay, or like a class. Like you gotta have a benchmark, right? So okay, so in my 15 year of teaching, there's a class or student that I thought like super smart. Okay, so based on that benchmark, like yeah, you guys fit into the category, right? So so that's what this is. So how the potential energy being set up, a lot of times is what? A lot of times is what, guys? Okay, so for like in chemistry, right? So potential energy is what, guys? When they're infinitely apart, okay? That is where the benchmark is. They set that as what? 0 potential energy. Okay, 0 joules of energy. That's the benchmark, okay? And then, okay, so when they create a bond, what happens, guys? They come closer, closer, closer to make a bond. What happens, guys? They will be releasing energy because they become more stable. Potential energy what? Goes down when they become stable. What happens, guys? When they come closer, they drop down. Okay, potential energy goes down because why? When they create a bond, potential energy goes down. Okay, so that's basically, guys, explains, okay? Threshold of 0, the benchmark potential of 0, okay? So they're not gonna ask, it's more of a physics question, by the way. Okay, the equation really comes down, guys, from the equation, potential energy equation, guys, okay, which is like K times Q1 times Q2 divided by R. That's the equation for this, but again, it's not for us, it's okay. And then, for example, guys, like, so this right here is where they want to be at. Okay, they want to have a lower potential energy when they create a bond. That's where they want to be at. Okay, so now, okay, but if you bring them too close, it's not really good that the energy goes up like that. Because why? The nucleus starts to repel. So the sweet spot, which is like right there, that's when the ideal bond has been created between two atoms. Okay, and that bond is what we're discussing today. This bond can be anything. Covalent bond, ionic bonding, whatever the crap that the bond is out there, okay? So that's basically the graph, and they want to discuss this graph a lot. Okay, so So what kind of questions they can give you guys, for example? So, oh yeah, by the way, there is a graph like this, but more like this. Okay, there's a graph that looks like this. Okay, so and they give an example. So we have, for example, Cl2, okay, and for example, we have F2. Chlorine gas, okay, and fluorine gas, okay, FCl2, F2. Which one is it? That's some of the questions they give you, for example, okay? So, as we know, guys, Cl is a larger atom, so when they make a bond with the other Cl, the fluorine with the other fluorine, what happens, guys? Okay, so this is a larger molecule, which is what? Larger atom, which means what? The bond is what? Longer, okay? The internuclear distance will be what? Greater. So this is what? Cl. That's a fluorine. So questions like that will be given from a graph perspective. for a question like this, okay? Only on the AP. Like, I have not seen anywhere ask this question, by the way, okay? So sometimes also they give you like, you know, a graph that goes like this, much lower, for example, guys. And okay, so if it's much lower, like dips down lower, much lower potential energy, now what the hell do you know about this one? This is what? Stronger bond. Stronger bond, okay? Which means what? This could be what? More like N2 gases, for example. Nitrogen gas. And now I'll teach you guys how to draw the Lewis dots and stuff. I mean, you guys already know that, by the way. N2 gas does what, guys? Triple bond. Okay, so triple bond is what? Dude, they got more energy, okay? There's more stability there. N2 gases. So something like that, guys, is where the college wants you to definitely know, okay? In terms of dipping of this graph, they ask a lot of questions in this one. So like, dude, like if you think about it, right? 70% of the atmosphere is N2 gases, okay? 70% is N2 gases. Why are there so many? Yeah, why are there so many, guys? Because why? It's hard to break. If you want N2 gases to react, what do you have to do? You gotta break this bond. Bond has to break, okay? But it's hard to break them. That's why they never react. So, like, you know, N2 gases, guys, there's a very small usage of the N2 gases. Like, only time that I can think of, guys, that the N2 gas can be used for something is a nitrogen fixation in bio. Okay, it's the only time like this can be something that would be worthwhile to discuss. So basically, guys, you know, like understand this graph, guys. By the way, so internuclear distance versus potential energy of the atoms and such. Okay. All right, let's take a look at, guys. The easy one first, okay? Which I'll discuss ionic bonding first. So what I'm doing right now, guys, in terms of ionic bonding, you have to know it. I'm not kidding, guys. Like I'm not just doing this for the fun, but you definitely have to know for the AP. Better to know it than not. Okay? I mean, can you get by without knowing? Yes, but it's really good to know what I'm doing right now, and you be able to replicate this process. Okay? So, I mean, you guys know what ionic bonding is, right? So, ionic bond. So not every time, okay? But it's what typically between what? Between a metal and non-metal. Metal and non-metal. When the metal and non-metal react, okay, they tend to what? Create ionic bonding. So by definition, guys, which college board doesn't want to talk about it too much, guys, so the definition of this, by the way, like when you create ionic bonding is what? When two elements, okay, like it's a binary compound, right? Binary means like two elements reacting, like, you know, turns into a compound, for example, guys. And when the two elements bond, okay, and when their electronegativity between the two is greater than, difference is greater than 1.7. So electronegativity is what, guys? Like we talked about, right? Definition, right? How strongly the element or the atom is attracting a bonded electron, right? That's what we talked about, okay? If the value differs more than 1.7, okay, so this guy is, for example, like I don't know, 1.2. This guy is like 5 or something. If the value differs more than 1.7, okay, then they create ionic bonding, okay. So that's what the definition is. But do you have to memorize these values for all the elements? Absolutely not. Okay, that's not the case. You don't have to. Okay, you might have to know the trends. Okay, fluorine is the highest value, oxygen number 2, chlorine number 3. You know, like you have to know basic trends, but you don't have to memorize numbers. Numbers is not something they ask to memorize. Okay, but typically, so that's what they say. Okay, if you have a metal and non-metal, it's ionic bonding. Very simple. Okay, they keep it simple like that. Okay, so yeah. But there is I don't know, man. Like there is you know, like students get confused. For example, guys. They give you like stuff like this, okay? Like even like, dude, I tell you, even I get confused, man, sometimes, okay? They give you stuff like this, okay? So like, okay, so they think, okay, so aluminum with the Cl. So what I'm saying is this, okay, BCl3, right? If you, this is actually, guys, a molecular compound, okay? This is covalent bond, okay? While this one is not. So which means, guys, I mean, we understand, guys, I mean, if you look at the periodic table, like, dude, I tell you, man, even I get confused on this one. So, but AP guys, they'll be very clean cut. They'll be very clean, transparent on this one, guys. There is well, there's a line of metalloids. So on this side is all metals, on that side is all non-metals, right? So whatever that's on here, it's like big question mark. Okay, are they metals or not metals? What the hell they do, right? But now, boron sits right here. Okay, aluminum is like underneath this. Okay, I mean again, found a mistake, right? So like, okay, so which one is it? You know, like it's like, oh my God, you know, I don't know what to do. Aluminum is a metal. This is a non-metal. So yeah. Okay, so like, you know, this is not going to create a ionic bonding while this one is. Okay, so it's hard to tell on this line. So yeah, but you know, unless you're taking like Olympiad Chem or something, okay, they're not going to play around this. But you got to know a few. This one is a metal. Just keep that in mind, okay? And this one is what, guys? Non-metal. At least for now, just have to know those guys, by the way. Okay. And like electronegativity difference as well, guys. I mean, the electronegativity is higher for boron compared to aluminum, so which means they will create, you know, like ionic bond. I mean, more of a covalent bond than ionic bonding, for example. Okay. So you know, but keep in mind, guys. By the way, you know, between a metal and non-metal, guys. So any one of these guys versus that guy is what will create ionic bonding. Because what difference of the electronegativity values. Sometimes there's a little question mark, but again, it'll be clean cut for our AP exams. Okay. Your teacher, who knows, man. So I don't know. We'll see, but you gotta follow your teacher's way. But now, so the formula, guys, right? Like very easy stuff, by the way. For example, guys, so metal, like the formula, right? So when it was a metal, guys, for example, like calcium. So when it's very simple stuff, right? Calcium and chlorine, for example, guys. So like one of the few things, guys, you have to know for the regular chemistry, that stuff you probably took in 9th grade or 8th grade, I don't know when, or last year. Is what, guys? Like calcium. So keep in mind, guys, yeah? The purpose is what, guys? Purpose is the octet. Octet is the purpose, right? So calcium is what, guys? Calcium has 2 valence electrons. They want to get rid of the 2 valence electrons, right? It becomes 2 plus charge. Okay, because calcium will lose 2 plus, right? So is what, guys? They have only 1 electron they want to fill in, minus. So one of the things you have to know is what, guys? When you have ionic bonding, what happens, guys? Yeah, when 2 plus and minus forms, what happens, guys? The formula becomes what? You gotta balance the charges, right? You need 2 of these guys, by the way. Calcium chloride. That becomes the formula, right? So it's very basic stuff. Yep.
How do you know how many valence electrons calcium has?
Because calcium is on. Remember, like this is the first column, right? Yeah. And that's the second one. So basically, as per our discussion here. You know, this is what? This is the, you know, if you find an atom here, it's what? It's got 1 valence electron. This is what? 2 valence electron. Like here, 3, like 4, 5, 6, and 7. And also, if you think about it, right, here as well. Like if you look at it here, it's like you got 1 electron on the S, okay, 0 electron on the P. You know, that's based on the electron configuration as well. And you got this one has a 2 valence electron because what? It has 2 electrons from the S. And if you look at these guys, like Cl, for example, is what? Okay, so you have what? 5 electrons on the P, 7 valence electrons. So you can, based on the placement of where they're at in terms of periodic table, you can tell how many they got. So this is like, you know, something not you guys for you guys, by the way, but absolutely, guys. This is one of the questions they can ask you with when you're getting the formula for the compounds. Okay, but now, first thing first. Okay, this is where. It's being recorded, so you guys can go back and take a look at it if you want to. This is not the reading I provided, guys, by the way. There's a name for this process, by the way, I forgot. But you have to know, okay, step by step, how you create this. Just so you know, you gotta know the step-by-step process. Okay, so how ionic bonding is produced from a calcium and chlorine, okay? Like, you know, step by step, what happens? Okay, it's not like boom, calcium gives 2 electron here, and then turns to that guy, game over. There's a certain steps involved in this, okay? And that's something they will ask you. Okay, so I'm not going to calcium because I'll use sodium. Sodium and Cl, sodium chloride. So let me do that step here, guys, by the way. So first thing first, guys, by the way, to explain this, I'm going to write the equation first, okay? The equation is sodium solid plus half of Cl2 gas turning into NaCl solid. Okay, that's the equation right now. Okay, So producing one NaCl solid ionic compound from its element, sodium solid, okay, half of Cl2. Okay, it's a balanced equation, okay? And you know, like down the road, you guys will know, guys, this kind of equation, guys, and again, maybe I mentioned, I mean, some of you guys, this equation is what, guys? It's what we call formation reaction of NaCl, okay? Where you're getting one molar compound from its elements, okay? The delta H of this reaction is what we call, guys, a formation reaction, okay, of NaCl. The formation, like keto formation of NaCl.
Wait, what are those small letters? I can't really read it.
Heat of formation.
Under the H.
This is
No, sorry, under the H. And above the H.
this one?
Yeah.
So R and X represents reaction.
Oh.
Yeah. I mean, at least like I don't know. That's how I was taught in college, by the way. That's why I use this. Your teacher might not use that. Okay, so let's take a look at this, guys. Okay, so this represents, guys, okay, potential energy. Okay, so again, I'm sure, guys, I can't finish this topic today, by the way. Okay, potential energy here, guys. Okay, so first, guys, I'm going to start with the Na plus. Okay, Na solid with this half of Cl. So I'm going to start off here. That's where their energy is at right now. Okay, so here, guys, I have Na solid. Okay, and half of Cl2 gas. Okay, that's what they come in nature. Okay, Cl2, guys, again, is diatomic gas, right? So Cl2, guys, I mean, they come as a pair, as we know, guys. Okay. So the first thing first, guys, by the way, okay, in order for them to react, so you might say like, what the hell? But in order for them to react, guys, the first thing that occurs is so basically the next step is this. This is step one. Step one is, guys, I'm turning the sodium solid into a gas. And you probably think, what the hell is this guy doing? This is a step that you have to know, guys, for the formation of ionic bonding, okay? That's why I'm doing this. There's a name for this process, I forgot, okay? That's the first process, okay? Sodium solid, so all I did is what, guys? I turned the sodium solid into sodium gas. That's all I did, okay? So now, what is that process called, guys, by the way? So if you turn something solid into a gas, guys, what do we call that, guys? Sublimation, okay? So process one is what, guys? Sublimation of sodium solid. Okay, so keep in mind, guys, dude, like I tell you guys, okay, if you're turning something that's a solid into a gas, energy must be put in, right? Which means what? That is an endothermic process which requires energy to be put in. Okay, so it's endothermic process what the potential goes up. The first process. And the second process is Na plus gas plus electron, okay, plus half of Cl2 gas. So basically what happened, guys? I turned it into Na plus now. This is step two. Okay, what's a step two, guys? What can we call that process, guys? Step two is what, guys? So I turn sodium gas into a Na plus electron. What do we call that process? We talked about it last week, guys, which is what? Ionization, okay, of sodium, right? So there's what, guys? Ionization. Okay, so that's what. So again, we talked about, guys, you're removing a valence electron from a sodium, okay, which is an endothermic process as well. Okay, you're taking the electron out, and the process where the potential goes up. Okay, so now sodium is ready. Okay, when now the Cl is ready, because what? So I have a sodium gas now, Na plus gas. Okay. So now the next step is what, guys? Cl2. I gotta work with the Cl2. I gotta turn it into Cl minus, right? But now the problem is what, guys? Cl2 come as what, guys? They come as what, guys? Diatomic. Right now, Cl2 looks like this. They're diatomic. We'll discuss this later, guys, for the bonding and stuff. They come as this. We gotta break this bond, okay? Because Cl cannot really. They're not too bad right now, guys. They're like, okay, so I'm not gonna react. Why would I react? Okay? So we gotta turn them into what, guys? We gotta break this bond, and we'll turn them into what? A chlorine atoms. Okay? So that process, guys, basically what I'm doing is, guys, this now, okay? The next process is, I have Na plus, which I'm not doing anything with this guy anymore, plus electron, and now it turns into a Cl gas atom, okay? It's not Cl2 anymore, okay? So that process, what, guys? Process 3 is basically what, guys? That's what? Bond, so I'm breaking a bond, okay, between the Cl2. And now, keep in mind, guys, here, by the way, energy needed to break a covalent bond is called bond dissociation, okay, of a bond. So it's called bond dissociation of Cl2. So bond dissociation energy is the amount of energy needed to break a covalent bond, okay? So keep that in mind, guys, by the way, okay? So energy must be put into break a bond, right? So that's why energy goes up. And now the Cl is ready to get the electron, right? So Cl, okay, so what will happen is what? Cl is going to get the electron, okay? And then what will happen is what, guys? So once a Cl gets electron, it will lower the potential energy, guys, by the way. So electron energy drops down. And what you get is what, guys, here? Na plus gas plus what? Cl minus gas now. So what do we call this process? This is step 3, this is step 4 now. So what do we call this process, guys? An element gains electron, okay, and becomes Cl minus now. What do we call that process, guys? Electron affinity, okay? This is what we talked about, guys. It's the definition perspective, guys. Which is what? What is this, guys? Amount of energy released when an element gains electron in the gaseous state. That's what we call electron affinity, right? So, and then again, it releases energy. Okay? That's why it's an exothermic process. That's why what? Potential energy drops, become more stable. So now I have nicely, guys. Okay, I started from here. I have what? Na plus and Cl minus now. Okay. Where do I go from there, guys? They will bond. Turn into what, guys? Turn into NaCl solid. Okay? 5. Hey, well, this step, guys, this is on the AP, actually, just so you know. Your teacher might not even do it. 5 is what, what do we call this, guys? Very, very important, guys, okay? Lattice energy. Lattice energy. Okay? So what the hell is lattice energy, guys? This lattice energy represents what, guys? Actual energy that what? Needed to break an ionic bonding. So this is like, dude, think about it, guys. Look at the opposite process. Let's assume, guys, you want to break the ionic bonding, separate these ions, okay? That's the amount of energy you need to put in, which is what we call the lattice energy. So, okay, I'm gonna, not going further for that one. And now from here to here is what, guys? Delta H of what? Formation. Okay, so which is like over there. You see that, guys? This is something you have to know for the AP. I'm not kidding, guys. You guys, you gotta know this one. Like steps of creating the ionic bonding from element phase. Okay, it's not, oh yeah, like you're like whatever you did. Okay, by the way, okay, so NaCl magically comes into NaCl. No, it follows a bunch of steps that we discussed. Okay. Keep in mind, guys, here. Dude, I tell you, man, by far the most important thing is this guy. Understand what this is. So lattice energy directly is in line with what, guys? The strength of the ionic bonding. It's like, dude, like what, dude? Strength of a bond depends on what? How much energy you have to put in to break them, okay? And that represents what, guys? How much energy you have to need to break them in, break the bond, right? So let me tell you something, okay? So one thing that I really don't like, guys, from bio. Okay, which I don't know where you came from, by the way, so I don't know what kind of science you did. But in bio, right, what do they keep on saying? In bio, a lot of times they say covalent bond is stronger than ionic bond. They say that a lot of times, like, what's the strongest bond? Covalent bond. I tell you guys, okay, can you compare that, guys? Can you compare covalent bonds to ionic bond, guys? You can't. Because why? Strength of bond depends on what? How much energy you need to break them. Okay, so again, this is like for you and me, guys, in chemistry perspective, okay? We're not in bio anymore. So if you look at it, right? The bond So the strength of bond depends on how much energy to break them. Ionic bonding is what, guys? Lattice energy. Covalent bond is what, guys? Bond dissociation. Can you directly compare the two and say, oh yeah, because of this is greater, we're gonna say covalent bond is stronger? We can't. You cannot say that. Okay, so you're comparing an orange to an apple. Oh yeah, which one tastes better? This one's sweeter, so yeah, I like this. That is not a comparison. So yeah, so that's one of the things I don't like about bio guys, by the way, because they put a weird stuff on certain questions, by the way. So you can compare lattice energy to lattice energy. Okay, strength of NaCl versus MgCl2. You can do that. You can compare NaCl to MgL. Ionic bond to ionic bonding. You can compare those two, but you cannot cross compare. Like, oh yeah, by the way, okay, Cl2 covalent bond versus NaCl bond. You cannot do that. Okay, so yeah, because that's covalent bond, that's ionic bonding. So in chemistry, guys, at least from the AP Chem perspective, they will not compare the energy of these two. They will never do that. So that's like something you probably see in the very like low level bio, I think. They do that even like in the AP bio too, just so you know. So so whatever. But you need to know the steps. I'm not saying you should need to replicate what I'm doing. Oh yeah, draw this diagram for me and label them all. I'm not saying that, but you gotta know, what the hell's happening. Because some of the questions will be in the test. The AP exam, guys. If we were teacher guys, who knows? What the hell your teacher's gonna do? I'm not sure. But the steps here, you gotta know. So what kind of questions they can be getting, guys? You guys getting is this. Question that they've been asking is this. So NaCl versus KCl. Okay? Which one has a stronger bond? That's what they're gonna ask you. Okay? Aside from this diagram that I drew guys here for you guys here, they'll ask you, oh yeah, if you compare this guy to that guy, which one has a stronger bond? That's a question they can ask you guys. What do you think, guys? So it could be many things, right? So again, strength of a bond depends what? Depends on energy needed to pull them apart. Okay? So the one thing they will talk a lot in chemistry is what? The Coulombic attraction. That's what we also talked about it in the previous chapter as well, right? Attraction between what? Plus charge and minus charge. So keep in mind, guys, here, by the way, in chemistry, any bond or attraction that you see is between what? Plus charge and minus charges, every time. Okay, there's no other attraction. So again, the Coulombic attraction is what, guys? The equation goes force of attraction is equal to, guys, K times, K is a constant, it's a number. Okay, you don't have to be concerned about those, okay? If you guys take like AP physics or something, guys, then you gotta memorize this number, by the way, okay? But for you guys, like AP Chem, man, no. Charge 1, Q1 times Q2 divided by R squared. That equation, guys, you might as well memorize this equation, guys. I mean, it's not that hard, by the way, okay? So one positive charge, one negative charge, okay, distance between the two, R, okay? How far are they away from each other? That's what the equation represents, okay? So, for example, guys, this is a positive charge. That's a negative charge. Negative charge is bigger, as we discussed, guys, by the way, because if you gain electron, they're larger. The distance is what? Always from us. Center of one to the other guy. Center of the other guy. That's R. See that, guys? So now, if you compare these two, what do you guys know? Okay, so if you look at it, guys, by the way, the charge is all the same. Okay, plus 1, minus 1, plus 1, minus 1, right? What's the difference, guys? R will be different. Because why? K plus is a bigger atom compared to what Na plus. Okay? So if you look at it, guys, I mean, so if I draw here, the K plus is a bigger atom compared to what? Cl minus, right? So which means what? The R value is greater for KCl, which means what, guys? The Coulombic attraction between K plus and Cl minus is weaker, result in what? Result in lower lattice energy, smaller lattice energy. It's easier to what? Break K plus and Cl minus compared to what? Na plus and Cl minus. So you gotta bring in Coulombic attraction and lattice energy to explain why NaCl has stronger ionic bonding compared to KCl. You know what I'm saying, guys, here? So keep in mind, guys, like, it's very simple if you know what the hell is happening, okay? But it'd be very difficult if you don't know what's happening. So, it's not that hard, man. And also, guys, they have questions like this. Yeah, I'm not kidding. You know what? These questions, guys, they ask on the chemistry Olympiad also. Like, dude, like, every time they have a question on this one, and every time the answer is what? MgO. Magnesium oxide. Compare NaCl, Mg to MgO. Okay, so if you look at MgO, what happens, guys? Their charge is what? 2 plus, 2 minus. You see that, guy? It's like Mg 2 plus. There's what? This is Fuego, alkali earth metals, right? So okay, so the size, they're next to each other. Size is very similar, and this is smaller, by the way, also as well compared to Cl minus, right? So what happens, guys? Because of the Coulombic attraction, this guy got plus 2 minus, and their size is about the same, right? This has what? Stronger Coulombic attraction result in what? Greater lattice energy, which means what? This will have a stronger ionic bonding. Okay, do you understand what I'm saying? So, okay, so let's talk about this, right? So if you have a stronger ionic bonding, right, what does that result in as a physical properties? What the hell is physical properties? The boiling points, the melting point, and stuff like that, right? Because of that, what happens, guys? Typically what, guys? The melting point should be what? A lot higher for these guys compared to an ACl. Do you understand what I'm saying, guys, here? So, yeah, so having the higher, stronger bond means what, guys? Yeah, melting point should be higher. So, dude, I tell you, man, like, I don't know how they teach this guys in the lower classes, by the way. You know, like, dude, I tell you, man, I've been doing this for like how many years now? Like 15 years, guys. I've been teaching guys, okay? And like, dude, I saw like many things, okay? So I don't really, guys, like do like one-on-one tutors anymore, guys. By the way, because I passed that, you know. But like, I've seen some teachers, like like teach the class, like in school, okay? Like, what is like they teach like this. Oh yeah, the valence electron like this, right? They draw like, oh yeah, like okay, so this goes here, like there's a certain diagram going on, okay? I mean, I'm not saying it's wrong, okay, but you will not have to do that for AP, okay? So so that is like past us, guys. I don't think, guys. I mean, I don't know if I have to, guys, teach you guys how to draw the Lewis dots like for the elements. I'm not sure, guys, by the way. But again, but for us, like just keep in mind, guys, like what's happening, guys, and this is like more on the AP level. So I'm not teaching these stuff, guys. There's a lower class. If you find this very difficult, by the way, there's like a class on Tuesday, Thursday, which teaches like regular stuff, by the way. Okay? Which like I don't know who teaches it and stuff like that, but they teach a little bit like more fundamental level, guys. If you find this like absolutely like what the hell is going on, then you might want to entertain it with that class, by the way. I'm not saying like discourage you, by the way. Yeah? Because I'm skipping like these things. And like, oh yeah, here, like coming there. I'm not doing that, okay? Any questions, guys? Let me know. Any questions, concerns? Okay. So guys, that's ionic bonding, okay? Well, let's talk about, guys, some of the properties of ionic compounds. Very simple stuff.
Can I go to the bathroom?
Yeah. Use the bathroom, guys, before we come to class, okay? Guys, use the bathroom before we come to class, okay? So like this guy probably come back in like 10 minutes now. All right, so properties. Okay, properties of ionic compounds, okay? Dude, like, I don't know how much you guys pay for these classes, by the way, but like, you guys pay like every second matters, okay? So do I do you guys break? Absolutely not, because, dude, like, I see it only once a week, and I don't know, like, freaking, like, I don't get it. I don't understand. All right, so properties of ionic compound, guys, okay? So, like, properties, okay? Like, meaning like physical properties, okay? So physical property means what, like melting point, like density, like boiling points. Those are like physical properties, just so you know. Okay? Like conductivity, for example, guys. Like those are physical properties on the compounds. Very like like simple stuff. Okay. So one thing to note is what these Coulombic attractions, right? Aside from what you learn from bio, okay, very strong attraction, by the way. So these electrostatic force of attraction between plus charge and minus charge are very strong, okay? Which means what, guys? Like, it's hard to break them apart, guys, which means what? They have a relatively strong force of attraction. Because of that, they're a lot of times found as what? They're found as solids, okay? So ionic compound like salt, right? So a lot of times, guys, ionic compounds are being called salt. So salt is what, dude, they are coming as solids, like NaCl, right? NaCl solid, okay? So because why? Strong ionic bonding, okay? They're not, I've never seen, man, like a liquid ionic compound, I've never seen them, okay? And because of that, guys, very strong force of attraction, guys, and it takes a lot of effort to separate them. What happens, guys? They have what, guys? They have a very high melting point and boiling point as well. So they probably have what? They have like 1,000 degrees Celsius. You have to bring up to 1,000 degrees Celsius to make them melt. Okay, very high melting points. Okay. Yeah. What about their solubility? So this is like, you know, like. So this is a little bit of a touchy subject because solubility has a lot to do with, guys, the element itself and the process of dissolution, okay? So I can't really say for all, but there are some ionic compounds that are very solid in water, okay? Which means what? They break in water, they dissolve and dissociate in water very well, okay? So there's a term, like a slang term that you guys know, which is what? The light dissolved light, right? So water is what, dude, like water is what? A polar substance, right? Like water is what, guys? Like, you know, very polar, yeah? So these ionic compounds are what? They dissolve relatively well, okay, in polar solvent, okay? So, you know, so which means what? Like ionic compounds, which has a permanent plus charge minus charge, what? They dissolve well in water, okay? Solubility perspective. Some don't, okay, but not all, okay? Some can dissolve really well, you know, based on, you know, like, you know, that's something later, guys, okay? But relatively, you know, they dissolve relatively well, you know, in water. And now, conductivity. This is where a lot of questions began, guys. Conductivity. Not that, like, dude, like, not that you guys have to learn up to the level of, like, physics, guys, by the way, like moving currents and stuff like that, guys, conductivity. It's a conductivity of what, guys? Electricity, okay? So, for example, guys, I mean, again, if you guys have salt water, okay, water, salt water, guys, what happens, guys? I mean, they are conductive. So, it's like carrying currents, by the way. So, in order to be conductive for a substance, what happens, guys? They need to have a moving charges, okay? Moving charge particles. So particles have to be able to move from point A to point B, okay? That's basically what you need for conductivity. This is like electrical conductivity. So this is tricky, guys. And they have a lot of questions on this one a lot, guys. So as a phase perspective, solids, liquids, and gas, not gas, there's not really gas for ionic compounds. And also aqueous. Aqueous means like dissociated water. So keep in mind, guys, by the way, okay, because, dude, like ionic compounds, they have charge. They have plus and minus charges, right? But as a solid, these charges cannot move. Which means what, guys? Solids are not conductive. Keep that in mind, okay? But now, at a molten phase or aqueous phase, they are conductive. They can move around and what? Conduct electricity, right? So keep that in mind, guys, by the way. So, like, you know, a lot of times the question can ask you guys, oh, this substance, whatever this thing is, okay, has a very high melting point, okay, and it dissociates relatively well in water, and then it has what? It's conductive at a liquid and aqueous phase. Which one is it? You pick an ionic compound, okay? That's what it is. Because those are some of, you know, what we call, guys, what? Like, this is what we call, guys, you know, like, you know, physical properties, right? And also, like, they also might bring up, guys, thermal conductivity. Okay, thermal conductivity, okay? So the coefficient for the thermal conductivity for ionic compounds is relatively low. They're not a good thermal conductors, by the way. So if you, like, dude, if you touch like here and here, guys, for salt, guys, I mean, yeah, they're not really good at it, because, you know. So they're relatively considered as insulators, by the way, okay, rather than a conductor of heat, okay? So those are some of the examples, guys, of the ionic compounds you guys have to know. Any questions, guys? No. this is like anti-compounds, by the way, guys, is like 10% of the bonding chapter, by the way. So the other 90%, you know, is about the covalent compounds. This is like nothing compared to not really nothing, but the volume of the questions you'll be getting, guys. A lot is on the molecules and the covalent bonding and stuff like that. Yeah. All right, let's take a look at, guys, covalent bonding now. Okay, so I'll do a quick recap, guys. I'm drawing the Lewis dots for the molecules and stuff, guys. So let's discuss that a little bit. So, but before that, covalent bonds. All right, the covalent bonds, right? So covalent bond is for us, okay, for AP Chem, okay? It's always between non-metal to a non-metal. Okay, always between, always for you guys, non-metal to non-metal bond. That is covalent bond. Okay, if there's a bond from between non-metal to non-metal, guys, no question it's covalent bond. Okay, so like, okay, so meaning like what it means is you never have to memorize that electronegativity difference. Okay, so if it's less than 1.7, it's covalent bond. But again, like, okay, so it's always non-metal, non-metal. So just to let you know, guys, by the way, you have to ask yourself, guys, can metals create covalent bond as well? Yes, they can. Absolutely no question, guys. They can do it. But that is not in the scope for you guys. That is, so to understand that, okay, to understand a metal and metal covalent bonding, guys, you gotta know molecular orbitals. You gotta have some background in those. That is not in the scope of the AP. They don't talk about it. Okay, so that is not something you have to be concerned about. So whenever they talk about covalent bonding, guys, between these guys, okay, like nitrogen and fluorine, oxygen, and stuff like that. Okay, and metals will not participate in covalent bonding at all, guys. I guess we know. So you know, so what is one of the things, guys, you have to understand is like covalent bond is what? Sharing of electrons, right? Like that's where it comes down to, guys. So I think, I don't know, man. Like it's a hit or miss, I think, in some cases with these things. But you have to know. I had a problem with this for the last year classes. Okay, last year class was like absolutely a joke because of the COVID learning. But I had a students where they have a hard time drawing the Lewis dots. Like towards like the end of AP, guys, like they take the AP exam. Like, I mean, it happened to all of my students for the Olympiad as well. They can't draw the Lewis dots. And I was like, what the hell are you doing? All right, so drawing the Lewis dots, okay, that is, so I don't want to say that's not in the scope of the AP, guys, but you have to know how to draw the Lewis dot structures, okay? So that is something you should probably learn, guys, like coming into this class. But if it's really been a while, then we can kind of, you know, like refresh a little bit, guys, by the way. So I'm going to walk you through, guys, of drawing some of the Lewis dots and from easy to complex, okay? And then how I draw it, guys, and, you know, it depends on if whatever you're doing works for you guys, I mean, stick to that. You know, if you guys keep on getting it wrong or doesn't know what to do, guys, then you might want to follow what I'm doing, okay, by the way. So let's do the easy one first, okay? So these are all covalent compounds, okay? And sometimes they call this molecule. So H2O, let's show H2O and H3. It's very important to know how to draw the Lewis dots, by the way. Very, very important. It's very tedious, just so you know. Some kids like, oh, I don't want to draw it. But you got it. There's no choice, guys, okay? Okay, so let's do these first. Okay? H2O and H3, stage 4, CO2 and SO2. Okay? So, like, can you? So I'll just do it because of the time. All right. So guys, so when you guys have you know, molecules like this, guys, H2O and H3 and it's H4. Okay, but you gotta be able to draw the Lewis dots. So if you look at it, guys, so it's the first and first. Okay. When you're given a molecule, okay, whether it's a complex or like, you know, or simple, molecule always, they have a central atom. They have a central atom and the other stuff surrounds it. Okay, typically, okay, for like AP, right? So, but identification of central atom is something that you have to know. Okay, so what goes in the middle and what surrounds it. Okay, and now the typical rule is, okay, whichever, so you have a binary compound, right? Like, which is, we only have a hydrogen and oxygen here. Okay, typically the one with the lower electronegativity goes in the middle. Okay, so like, I mean, dude, like, so what I can tell you as an example is this. When three people wants to get in the backseat of the car, okay, like you got two siblings, right? Who gets in the middle, guys? The youngest one, okay? Because why? They put up a less fight, okay? Because the bigger brother or sister, you know, like, yeah, he's in the middle. So that's exactly what it is, okay? So they kind of bully the one with the lower electronegativity. They put that guy in the middle, okay? So you know, so that's the first rule, okay? But now the problem is what, guys? So can you put, so oxygen has a highest electronegativity, guys. Can you put hydrogen in the middle, guys? You can't. Hydrogen cannot be in the middle, because why? Hydrogen, keep in mind, guys, they have what? They only have one S. They got no, the first principle level, there's no 1p. What does it mean, guys? They can only make, hydrogens can only make what? One single covalent bond, that's it. They cannot make, like, you know, 4 bonds, that you guys have more. That's the reason why hydrogen cannot be in the middle, in any cases, okay? That's the reason why there's no option oxygen to be in the middle. So what you do is, oxygen goes in the middle, hydrogen will surround this guy. You know what I'm saying, guys? That's like, usually, you gotta have like a little blueprint here, guys. Okay, so that's like, okay, that's what's gonna be. And then what? You fill the electrons in. So the next step is, guys, by the way, is the, you validate or you count how many electrons are bonding. Okay, how many electrons are gonna bond, right? So that's what? Number of valence electron in total for all. Okay, so hydrogen has what? One valence of the two of them, right? So from hydrogen, there's what? 2 electrons that will bond. Oxygen is what, guys? 6 valence electrons. There are a total of what, guys? 8 electrons that are willing to bond, okay, or participate in bonding, right? So now with these electrons, what you guys do? You gotta what? Complete the octet. So with the covalent bonds, the minimum is what, guys? Octet. Octet is the minimum requirement. Okay? So when they're like pairing up, guys, the first thing and minimal, like the bare minimum is what? Octet. Okay? So like for example, guys, if you're applied colleges, okay, what's the minimum requirement, guys? Yeah, you have to be in high school and graduate, okay? You gotta have some like, you know, score in GPA, right? Or something, okay? That's the minimum requirement, okay? So let's try to fill the electrons in, guys, by the way now, okay? Octet, 8 electrons around it, guys. So 1, 2, they have to share because they only have 8. Okay. So 1, 2, 3, 4. And now hydrogen, right? As we said, there's no like 1p. They're one bond and that's it. Okay. They have 2 electrons, that's it, okay? So oxygen gets the other. Okay, 1, 2, 3, 4, 5, 6, 7, 8. That's it. That's the loose dot for H2O. Okay? So oxygen here got 8 electrons here. Hydrogen got what, guys? 2. Okay. So they're sharing, these electrons are being shared. You understand, guys? Okay? That's what it looks like. Okay? And these are what, guys? What do we call this, guys? Lone pair of electrons. Okay? That's what they call it. So the drawing of this, guys, basically looks like this. Oxygen, hydrogen, hydrogen. So you gotta draw these guys. Okay? So, and again, like I'm not gonna go into shapes right now, guys. Like, it's a bent shape, by the way, but you know, so I'm not gonna get into too much about the shape, whatever, guys. Okay? So if you draw the NH3, guys, same thing. Nitrogen in the middle because hydrogen cannot be in the middle. So nitrogen in the middle, guys. Hydrogen surrounds it. Hydrogen has 3 electrons overall for the valence. Nitrogen is 5, so a total of 8 again. 1, 2, 3, 4, 5, 6, 7, 8. Single, single, single. That's what it looks like, guys, by the way. And the shape looks like that, guys. There's a lone pair of electron nitrogen, guys, and these guys have single bonds there, okay? And the shape of this guy is what? Trigonal pyramid. Okay? That's the shape of this guy. So whenever you guys have, okay, 3 bonds and 1 lone pair of electron, guys, that's what? Trigonal pyramid. Okay? Stage 4. Okay, methane. Okay, so this is what? Water, right? Ammonia is what? Methane gas, okay? Like when like cows like burp, like they get like this, you know? Like, you know, these two are what? What do we call these guys? What are they called? Greenhouse gases, right? Carbon Okay, I mean, so I'm not, like, you guys probably get the same idea, guys, right? That's my thing, get right there, okay? Stage 4. Very basic, okay? Like, dude, like, this is like, you know, like, relatively, I mean, I don't know if people say this, okay? So, which means, like, AT, guys, your teacher's not gonna run, like, okay, like, oh, this is how you should do it. They don't do that, okay? Because they expect you to already know this coming in here, okay? And then CO2, guys, okay? So, like, yeah, right now is what? I'm gonna give 2 minutes. 2 minutes, guys. Draw these. 2 minutes, guys. Draw these right now. Okay. CO2, SO2. They're relatively hard, guys. By the way, these are like super easy, by the way. But draw these two guys based on what I said in terms of what was in the middle and stuff like that. Okay. And complete the octets. I'm gonna give you guys 12:28, guys. In 2 minutes. 12:30. I'm gonna go over. Okay. Like guys. So CO2 and SO2. Okay. So if you draw a CO2, guys. Okay. So you gotta understand, guys, what goes in the middle? It should be the carbon, because the carbon has a lower electronegativity compared to the oxygen. So carbon in the middle, oxygen surrounds it. Right? And now you gotta count the next step as well. I mean, so whatever that you think you're doing works, don't change it, okay? But if you don't know how to do it, and if you're getting them wrong, then maybe entertain yourself to do what I'm doing, okay? So you gotta have the structure set up. And then, okay, so count the number of the electrons that are eligible for bonding, which is the valence electrons, right? Carbon's got 4. Oxygen's got 6, but there are 2 of them, right? So 6 times 2, right? Which is, 16, right? 16 electrons overall. So 16 electrons overall, you gotta complete the octet, minimum requirement, okay? So if you do so, guys, let's see, okay? So this is my recommendation, okay, for putting the electrons in. You typically want to fill in the outside ones first. You understand, guys? Okay? So, I mean, whatever that you've been doing that's working, guys, go ahead, okay? I'm not stopping you from that, okay? But if you don't know what to do, guys, okay, you fill the outside one first. So what I mean is this, okay? 1, 2, 3, 4, 5, 6, 7, 8, right? 8, right? 9, 10, 11, 12, 13, 14, 15, 16. I ran out. I ran out of electrons. Okay, 16 is what we have, and 16 is what I put in. That's it. So now, if you look at it, guys, okay, so oxygen has an octet, okay? This guy has an octet, right? Carbon has got only 4. That's a problem. You see that, guys? Carbon doesn't even have the octet. That's the bare minimum requirement for what? For bonding, okay? So bonding is what, guys? They want to have an octet. That's the purpose of bonding, okay? To be more stable. But carbon is what? They take all the electrons in, electrons like for the oxygens, guys, but what? They don't have enough. Which means what, guys? They have to share more than one electron. So oxygen have to contribute more for sharing. So instead of actually having lone pairs, they have to share those. And same thing on this side. You see that, guys? So which means what, guys? So for CO2, this is what you get. Double bond. You see that, guys? Any questions? Any questions, guys? This is linear. Linear, yeah? Like straight chain. Yeah.
It does it matter where the outer dots are put?
These guys?
Yeah, so like I put 2 on the left side and then like 1 on top, 1 on bottom.
That's mine. I mean, like where in placement wise? So what can be a good question on this one, guys? Yeah, what can you guys ask me? Yeah, what do you think a good question you guys can ask me, guys? What about this then? Can you do this? Triple bond on one side, double on one side, single on one side, guys. So we need like this. Can you do this? Sorry. Is this a possibility? What do you think? Can you do that? Is it possible? What do you think? Can you do this or no? Yeah. It's an octet. Yeah, think about it, guys. Like if you look at it, guys, right? 8, 8, 8. Right? What that? What do you think, guys? Is that something we can do? What do you think? Technically speaking, yes. Right? Like, yeah, you can do it. But now, will it be like this? What do you think, guys? So you gotta understand, guys, okay? So just kind of chime in, guys, okay? Here. Why is it not this? You'll not see this like this. You'll never see a CO2 like this. Okay? But you gotta understand why. Because I mean it completes job 10. I don't see any problem with this. Okay? 8 electrons on the oxygen, 8 on the carbon. Okay, what? And 8 on the oxygen here. Why this will not occur? Why you will not see that, guys? You gotta know, guys, for AP Chem, okay, you have to understand, you have to be able to draw the Lewis dot based on what? 4 mole charges. Okay? You gotta know this one. 4 mole charges. You gotta know what it is. You have to apply this when you draw the Lewis dots. Okay, so 4 mole charge, okay, so like it's octet is a minimum requirement, okay? But now for a bond. But 4 mole charge is like, okay, so if you guys apply for colleges, okay, you have to be in high school and like you're not failing out and like have some maintain a GPA, right? That's a minimum to apply for like, I don't know, some kind of college, right? You'll want to, like, this is like an SAT, you know, like an SAT like exam, okay? So it's like, okay, so if you guys want to have like, you know, more advanced bonding, double bond and stuff like that, you gotta count what? A 4 mole charge into an application process, okay? So what the hell is that? Now, how do you calculate this and what it represents? Okay, and also, you know, like, how do you apply this for the drawing the Lewis dots? Something to know. So, you gotta know for AP guys, you gotta know this one. You gotta understand what it is, how to calculate this, and try not to forget the equation, by the way. Okay. So, 4 mole charge, guys. Okay. Calculation perspective. Keep in mind, they will not ask you what 4 mole charge is. They'll ask you, draw the Lewis dot based on 4 mole charge application. That's what they're gonna ask you, okay? 4 mole charge is what, guys? So calculating perspective is what? Perspective is what? Is equal to number of the valence, original number of valence electrons, okay? So for example, guys, oxygens have what? 6 valence electrons from the beginning. So that's what you're starting from. Original number of valence electrons, okay, that's what you're starting off, right? Subtract, okay, number of bonds they created, number of covalent bonds. So now you got a single bond, 1 bond. There's one, you got triple bonds. You got 3 bonds, right? The number of bonds. Minus, okay, number of electrons that are not bonded. So these are electrons what? The lone pairs. Some electrons are not bonded, okay? Is equal to 4 mole charge. That's the equation. And then the desirable 4 mole charge, like oh yeah, what kind of SAT score do you want? 1600, right? Like 1600, right? The desirable charge is what, guys? It is 0. 0 is what they want, or close to 0. Okay? Like at most, like -1 or +1. Okay? Like -2, if you get a -2 or +2 or even higher, they're like, I'm not gonna do it. Okay? Like, oh, if you apply for like, you know, whatever to college and you get like 1,000, like, okay, no. That's what it is. Okay? They want 0. Okay? So now, let's calculate 4 mole charge for this. Okay, let's assume what you get out of this. Okay, for oxygen, for this guy. Okay, so you got 6 overall initial number of what? Original number of valence electrons. They contribute 6. Okay, minus how many bonds did they make? They made 1 bond. How many electrons there that are not bonded? 1, 2, 3, 4, 5, 6. Minus 6. What's the 4 mole charge, guys? Minus 1. 4 mole charge of this oxygen is minus 1. Is it happy, guys? It's like okay, so 1 foot in, 1 foot out. I don't like it, okay? Carbon. They got what? 4 initial valence electrons. They're in the 4th group, right? How many bonds? 1, 2, 3, 4. 4 bonds. 1, 2, 3, 4. How many lone pairs? No lone pairs. What's the 4 mole charge, guys? 0. So carbon is happy. Carbon, I don't care. Okay, I don't care if it's like this side, that side. I'm good. Okay. How about this one now? 6 minus what, guys? 1, 2, 3 minus what? 1, 2. Plus 1. 4 mole charge is what? Plus 1. So This one has a -1 formal charge. That guy has a +1 formal charge. So they're not happy, okay? Because like, dude, I want 0 as formal charge. I mean, I understand I got the octet, okay? But I'm not happy because why? It's not what? 0 formal charge. So what can you do? How can we fix this? Yeah, like with double bonds. Instead of having 1 triple, 1 double, this is what you got now, okay? Double bonds, okay? What do you got, guys, then? Okay, so you got 2 bonds, and 4 electrons that are not bonded. That's what? It's 0. Do you see that, guys? Same thing. You got 2 bonds, and what? 4 electrons, that's 0. Do you see that, guys? So everything has a formal charge of 0, 0, 0. That's what they want, okay? So outside from just the octet rule, guys, by the way. So for AP perspective, you gotta draw this as in the scope of what, guys? Formal charges. It's very important, by the way, okay? Questions, any questions, concerns? So let's draw. So where does a question like this come, about? So before that, guys, let's talk about SO2 first, okay? Sulfur dioxide. Sulfur dioxide, guys, if you draw this, sulfur in the middle, oxygen will surround it. Okay. 6, 6, 6, guys, that's how many electrons they have, guys. So you have a total of 18 overall electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, okay? So now, oxygen will have 8. This one has 8. This one will have 6 now. You see that, guys? And then it will, so at least an octet, so one of them has to create a double bond. Okay? So now the actual shape is single bond, double bond. That's what you get. Okay? That's the shape of SO2. Okay? So 1 lone pair. Okay? That's what you get. So yeah, so that one of the questions they ask a lot on this one. So even before you apply the formal charge and stuff like that, okay? You gotta look at this. So question they'll ask you on this. Okay, so when you draw this one, the shape is like this. I'm sure some of you guys already know what I'm talking about here. That's what you get, right? So now let's talk about these bonds, like double bond and single bonds. Let's talk about those guys. This is very important, guys. I mean, this is AP. Like really, guys. Okay, maybe your teacher didn't talk like for the lower level chemistry guys. Maybe you forgot. I'm not sure, guys. But now, let's take a look at these guys. So a single bond versus a double bond. Okay. Yeah. What do you guys think, guys? What do you guys think? Single bond is what, guys? Of course, what? It's a weaker bond, and what? And also, the bond is longer. Okay. Double bond is what, guys? Stronger and shorter. You know what I'm saying, guys? I mean, dude, like obvious, right? They're stronger and shorter. Okay. So now, if you compare, so dude, like based on the Lewis dot structure perspective, what happens, guys? You have a 1 single, 1 double bond based on Lewis dot. Okay. So then, the problem here is everything's based on the atomic structure of quantum mechanics. Okay. Like, oh yeah, S and P orbitals and stuff like that, guys. They got this. So, is this a correct structure? Is a question. Okay. So nowadays, guys, by the way, okay, people have devices. Okay, we have a device where we can measure the strength and length of the bonds. By the way, okay, we can actually measure. Okay, so what kind of bonds we have and stuff like that. Okay, so what they noticed was, okay, clearly based on the atomic structure, based on the Lewis dots, guys, these bonds are different. But is it different, guys, when they actually you look at the molecule? No, they're exactly the same. So this is a flaw to the Lewis dot structure, which is based on quantum mechanics. Okay, so which means, guys, they gotta fix this. Okay, so the way they did it, guys, is this. You gotta understand, guys. They introduced something called resonance structures. Resonance. So resonance structure is what, guys? Okay, to fix, okay, or to like a patch up, okay, things that are not in line up with what? Stuff that they are expecting from the Lewis dots based on the quantum mechanics versus what? Versus the real life molecule. Okay, so what they did is this, okay, like, yeah, what does it mean by resonate? Like resonance, resonate? What does it mean? Resonate? So, like, I don't know, like, So if they have a shape, like in bio, right? Like, oh, it resonates between these two shapes. So, like for example, guys, there's like enzyme, like, oh, enzyme shape can be like this, okay? Oh, sometimes the enzyme shape is like this, okay? It resonates between the two forms, okay? That's what it means by resonance, okay, in science, right? Like physics term, I'm not gonna talk about it, guys, by the way. So what they meant by a resonance structure is what? Okay, so they got this structure, and it, this is wrong, by the way. Okay, this is like completely just made up and just patching it up, guys. It resonates between what? Between this. So you got this structure and you got this structure. Do you see that, guys? So one thing about that. Okay, so one like, oh yeah, one time is this, the other time is this. It goes back and forth, 50% of the time you get find this, 50% of the time you find that. It resonates. So on average, what do you get? You get this. That's what you get. Okay, so it's the bond is what? They're exactly the same based on a proportion probability. Okay, this is what, guys. Like, it's not a double bond, it's not a single bond, somewhere stuck in between. That's basically what resulted from the resonance of the two molecule, the resonance of the molecule based on the bond in the single bond double bond. Okay, so this is they don't go too crazy on the AP. Okay, like AP guys, they don't really try to go make you guys go nuts on this one, because but example wise, every single time they give you stuff like this. Okay, like SO2, SO3. They always try to give you stuff like these two for the AP perspective to represent or to test you guys whether you guys know resonance structures. Okay, so like you gotta, I don't know how you guys got by, guys, for the other sonic chemistry did, but you have to know the formal charges, apply formal charges for the Lewis dot structure, and also the understanding resonance structure, guys. If you do not draw the resonance structures on the AP, they might be wrong. I'm not kidding, guys. They might be wrong. It doesn't matter if you draw the correct structure. If you don't draw this resonance, guys, they might be wrong. And sometimes they ask you, oh yeah, draw a molecule based on the formal charge, respecting formal charges. If you don't do that, guys, they might be wrong. So I'm not kidding, guys, because So make sure you understand what I'm saying, guys, by the way. Okay? Any questions, let me know. Any questions, concerns, let me know. If you want to learn more about this, guys, by the way, so they talk about something we call bond orders. Okay? So bond order. To understand that better, guys, you have to understand the something called molecular orbitals. Okay, that is not in scope. Okay, put your phone away. That is in scope. Is not in scope with the AP. Okay, so which means like this is something that they don't go too far as a bond order perspective. Because I mean, the teacher might, who knows, but. They don't push that far, so I'm not going to teach anything that's outside the scope of the AP right now, because what's the point? Any questions, anyways? All right, so let's draw, guys. We got a couple more structures. If you cannot draw the Lewis dot, guys, you cannot figure out like polarity of the molecules. It's very important to understand this. Guys, draw SO2, so SO3. Okay, and also SO4, 2 minus, okay? And draw the resonance if needed, okay? And also formal charge as well. All right, so SO3. So again, electronegativity rule first, guys. Sulfur has the lowest one, so sulfur in the middle. Oxygen will surround it. Okay, that's the first step. The next step is what, guys? Electron count, right? 6, 6, 6, 6. They all have 6 valence electrons overall. So 24, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Right? All done. What's up?
You said 6, 6, 6.
6, 6, 6, 6. 6
Is that 8?
6 times 4? The last time I checked was 24. Yeah. I mean, my math is going way, man, but I think 6 times 4, I think I can still do that. All right, so 8, 8, 8, and 6. Okay. Sulfur's not happy. At least octet, right? Like sulfur doesn't have the octet right now. Do you know what I'm saying, guys? Any questions, guys? So which means what? One of them has to be double bonded. single bond, double bond, single bond. That's what they got. You understand, guys? So if they ever if they ever give you this, what happens, guys? Make sure you give them what? 3 resonance structures. Okay. So you gotta draw one of this guy. Also, what you gotta draw this one, and you also have to give you what, guys? Also have to give you this. Okay. So you gotta draw 1, 2, 3. Okay. Resonance structure perspective, because all the bonds should be exactly the same. So you gotta, so make sure I didn't put the dots there, guys. But you gotta put the dots. Okay. I'm not gonna do that. So that's what's the answer for SO3, guys. Sulfur trioxide. So like you see that double bond one here, it's stupid. Okay, so, you know, like I don't like teaching this, okay, because it's the dumbest thing ever, by the way. So, but it's AP Chem, okay. So yeah, here, and here. You cannot forget this, guys. Okay, AP Chem. Any questions, guys? So the actual shape, but so like okay, so some of the students ask me, well, can I draw like this on the test, guys? Can I draw like, okay, so I know the actual shape is like this. Can I draw this? Don't do that, okay? Just draw these 3, very simple, that's it, okay? That's what college we're looking for. So guys, draw this one, guys, okay? So I don't know where you're at, guys, but draw this one for me, guys. You have to respect formal charges. I forgot what it was, guys. I think one of the students passed like fall. The student, I don't know, the teacher did something else, but you know, like trust me, guys. Okay, you gotta like they will say draw respecting formal charges. This will guys. We'll have to discuss something here. Okay. One minute, guys. All right, guys. Let's take a look, guys. Sulfur in the middle, oxygen surrounded. So keep in mind, guys, by the way, the rule is, if you see a 2 minus sign there, what does it mean, guys? It actually has 2 additional electrons, okay? So aside from like, so 6, 6, 6, 6, 6, okay? 6 times 5 plus 2, okay? Because why? It has that additional 2 electrons over there. Okay, that's one thing to note, which is equal to what, guys? This is equal to what? 32, okay? So you got 32 electrons, okay? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. So if you look at it, so unless you're like, it's not there, man, like math-wise, that's what it is, okay? So everyone's happy, okay? Do you see that, guys? Like there's a single bond, single bond, single bond, single bond. Everyone is octet, 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 okay? Everyone's happy, okay? Just on the octet perspective, this is a shape, okay? And then what? You gotta do a 2 minus there. That's the shape. You understand, guys? But, like, dude, is this enough for the AP? Absolutely not. But as in some teachers like, oh yeah, this is right. Next question. Like, no, you can't. Like, you gotta respect the formal charges. Okay? They will be asking on the AP. Okay, draw and respect the formal charges. If you do this, guys, completely wrong. So, what do you guys do? So when you do the formal charge calculation, let's see what you get. Okay? Look at this guy. I mean, so if you've done it correctly, guys, you get what? Minus 1, minus 1, minus 1, minus 1, and what? This, I think, plus 2. Okay, so I'm not gonna I'm not gonna count it, guys. Minus 1, none of them is 0. Do you see that guy? Yeah, dude, none of them is 0. Do you think they're gonna stay, guys? Do you think they're gonna bond, guys? Absolutely not. They're not. Okay, I'm not happy. So what will they do to alleviate this? Now, what do you think, guys? What the hell is he gonna do? What do you think, guys? This is what they do. So this is very, like, like AP, guys, okay? What they gotta do is what? Oxygen will share more. Double bond, and this one will make a double bond too. So you have a single, double here. They will make this guy 0. This guy, I mean, it's still -1. This guy will be 0 and 0. So that's how they reduce it down. So when you draw this is what you get. So you gotta instantly spot there's something wrong with this. Sulfur in the middle, okay? This is what you get. Yeah, what is wrong with this right now? Yeah, boy, yeah, what is wrong here? There's something wrong. What's wrong, guys? Sulfur is what, guys? Dude, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sulfur's got what, guys? 12 electrons around it. You understand, guys? The oxygen's got 8, like they got 8. This guy got 12. So it went beyond the rule of the octet. You understand? Do you understand, guys? So you think, okay, so octet, right? How did it go above 8? That's the question to ask yourself, right? So octet rule is actually what, guys? Superseded by what? The formal charge rule. You know what I'm saying? Okay? And is this even possible? Is the question to ask yourself. So yes, it is. The reason is what, guys? Sulfur is what, guys? It's on 3rd principal interval. Okay? So 3rd principal interval is what, guys? They have SP and D block. Okay? Which means what, guys? I understand, okay, these are typically valence electrons, I get it, okay, but they have an open D block, completely open, okay, not filled up. So, which means what? They can have up to what, guys? Up to 18 electrons in total, is why? Sulfur is in 3rd principal interval, okay? So, which means what? Sulfur is not restricted by that octet rule. They can have up to 8, that's fine. Okay. A lot of times, guys, formal charge supersedes the octet rule, by the way. Okay. So like, you get like 1695 on the GPA versus like 99 versus like 1300. Like that's exactly what it is. I'll take 1600 with 95 on the GPA. So like something like that, right? So, is this something, guys? Like you have to know? Absolutely no question. You have to know. Okay. So in that regard, you can have what? 12 electrons in the sulfur, and these guys have 8. So it accommodates the zeroth formal charges, -1, -1. So typically, if you can see, guys, when you add the formal charges, it becomes what? The total charge of the entire molecule. Typically, okay? So if it doesn't add up, guys, you did something wrong. So that's the shape, guys, by the way. Some teacher will argue with this, okay? So I don't know, like last year, man, like I said, some teachers doing some crazy stuff, man, but this is the shape, okay? What's your question?
No, I was gonna ask if you put the brackets in.
Yeah. You understand, guys? Any question there, guys? I mean, I don't know. What do you guys think about this one, by the way? But definitely formal charge is something you guys have to know, guys. This is above what you probably learned, guys, in the past year in chem, like whatever the chem you did, guys. I don't know what the hell you did, guys. But absolutely no question, guys. This is something that is scope for the AP, okay? All right, guys. Your homework, guys. I mean, again, I'm gonna send you a reading, okay? So you can't do the homework yet because not even halfway done, guys. By the way, so I'm gonna send you a reading for you to read, and there's some question in the back. You can do it if you want to, but that's not part of the homework, guys. And then, yeah, just do the reading. So I'll see you next week, guys.